That's so incorrect.
No, if you show all lone pairs, but you have your arrow coming from one of them, that's just as correct as showing the relevant lone pair. So there's two other lone pairs on this bromine, but they're not doing anything. So remember, I gave you this kind of example here. The lone pair on bromine that is relevant is held in this p orbital, or maybe a hybridized orbital, but an orbital that has overlapping symmetry with the pi star antibonding orbital of the alkene. It's this lone pair that occupies the antibonding orbital, breaks the alkene bond. And at the same time, the alkene bond has matching symmetry with the sigma star antibonding orbital of elemental bromine. So the alkene is breaking the bromine-bromine bond, while the bromine is breaking the alkene bond. And so you have all of these bond changes happening at once. Bromine-bromine breaking, two bromine to carbons forming, and the carbon-carbon breaking. I'm not ever going to grade you guys on transition states, not because they're too hard, but because I think they just steal a little bit from the focus of the class. But if you can go through a mechanism and predict or show all of the transition states, it usually helps to identify what bonds break and what bond forms. Then you can just take that list and demonstrate it. I break the CC double bond, I break the BR bond, I form the two CBR bonds. And that might help you remember what all arrows need to be in each step of a mechanism, what you need to show happening.
So in an intermediate, there should always be some charge.
That's a good question.
Like on the exam, are we asked to show the intermediate step and show the product? The product should have a charge on it.
If you're showing a mechanism, then yeah, you have to show all intermediates. I don't want to say all intermediates have charges. That's dangerous. But you're right that all of the intermediates we learned about have charges.
But this intermediate isn't like part of carbocation, is it?
There's no carbocation because carbon never holds the positive charge here. And this technically isn't an intermediate. This is the product. So this question skips the intermediate that forms after the bromonium ring, before the halohydrin. Do you guys remember what that intermediate is? Or what characteristic it has? OH2 plus bonded to the structure. It needs to be deprotonated in order to give the halohydrin. So you could think of it as the intermediate that forms is a protonated alcohol. You could think of it as water attached to the molecule. But there is an intermediate that's being skipped there. So if you were giving me the mechanism, this would not be enough. Starting material, bromonium ring, halohydrin product. Because if you're giving me the mechanism, that skips over a key intermediate. But this question isn't about the mechanism. This question is getting you to think about how the two stereoisomers form. Okay. Also, I'm not going to have you're not going to need to answer any questions about MO theory like this. But this is why I introduced MO theory to you. Because if all you had was valence bond theory, tell me why the bromine-bromine bond breaks. Why? Tell me why the carbon-carbon bond breaks. Tell me why the carbon-carbon bond is able to bond with the same bromine twice. You can't explain it, but if you look at MO theory, you can see bromine is donating electrons to 2 different carbons at the same time. Meanwhile, those carbons are donating back to bromine, breaking the bond to the other bromine. MO theory is what explains reactivity. It explains why some things are allowed and why some things are not. Okay, any other questions before we segue into Unit 5? Now, as a preview, at the end of this unit, your part B is not going to be predict a missing product and show a mechanism for the reaction. You will have one problem where you have to show a mechanism, and you'll have another problem where you need to solve a multi-step synthesis. That is, from this precursor to this final product, can you fill in a reagent that gives an intermediate followed by another reagent that gives the final product? You'll need to figure out what that final product could be made from, what that precursor can make, and find a route that links the two. Or in other words, from A through an unknown to C, filling in each of these things. That's our goal. So we're going to learn a lot more reactions in this unit. We're going to learn a few more mechanisms. And our application of it is to be able to do a multi-step synthesis. This is a fairly short multi-step synthesis, by the way. 2 steps, 1 intermediate. It's not uncommon to do 3 steps, 2 intermediates. If you guys start looking at your final exam, which is just a couple of weeks away, what I like to have on the final exam is a flow chart or a roadmap where you have a starting material and you take it through all of these different conversions to finally end up with a final product. You'll need to, at some points, just predict a missing product, given a reagent and a substrate, predict the missing product. At some points, you'll have to do a multi-step synthesis in order to figure out how can you go from here to here. So while you might not actually have to solve a multi-step synthesis like this on the final exam, it's usually embedded somewhere in that roadmap. You do have to do some sort of multi-step synthesis. One thing I like about roadmaps over just giving you a traditional multi-step synthesis is that you have the choice, or you have the opportunity to still earn points in a roadmap, even if you don't know all of the blanks. I might not have any idea what's going on over here, but I can still figure out what's going on here. There's almost never a reason to not get some partial credit in a roadmap versus a multi-step synthesis like this. It can be really easy to not be able to solve it, figure it out, and then just lose all of the points. So I like these because they test you in a very similar way, and they actually kind of give you a supportive hand. They show you how else to solve it, what else is going to be in there. All right. We're going to take our first look in Unit 5 at alkynes. First, let's just review some nomenclature. In terms of priority, an alkyne is tied with an alkene, which is higher priority than alkyl substituents and halogen substituents, but lower priority than alcohols. But if they're tied with each other, then what happens if they're both given the same locant set from different directions? This is just a simple 4-carbon chain. If I number from the left, my alkyne is at position 1. If I number from the right, my alkene is at position 1. Tie goes alphabetical. So who comes first alphabetically? Alkene. Tie goes to the alkene. And I think we've already seen this, but the suffix is given alkyne. So if we were to come up here and name our group, or name our compound, our root is bute, 4-carbon chain. But this isn't butine, it's actually butene-ine. And the alkene starts at position 1, and the alkyne starts at position 3. Bute 1-ene 3-ine. And I just want to clarify, that's the name we choose instead of bute 3-ene 1-ine. Let's do a couple of other practice problems. A word of advice in drawing alkynes. I know a lot of you are getting good with your zigzag lines at this point, but alkynes are linear. They're sp hybridized on both ends, so they should have two groups that stick straight out. I always recommend starting from the alkyne position, drawing your two sticks out from there, and then drawing the rest of your carbon chains. It might feel a little awkward because you often end up at kind of a weird angle, but I have a hard time grading when you draw something like this, because I know the alkyne is linear. So I see this as 1, 2, 3, 4, 5, 6. Because you've got this zigzag, but I know the alkyne is linear, so I'm counting 2 additional carbons, when what you want to do is 1, 2, 3, 4. So my advice, start by drawing the 3 bonds of the alkyne, and then just draw out bonds from there. If you're going to insist on drawing it geometrically wrong, then my advice would be make it impossible to think that there are any extra carbons there. Make sure that these show up very clearly. You could even honestly just go to bond line structure before trying to do something like this. This is just really challenging. What's the longest carbon chain in this compound that contains the alkyne? It is not 5. It's not 6. Remember that you cannot count both linear chain carbons and cyclic chain carbons.
So the first carbon on the triangle doesn't go towards the.
If this is part of a cyclic chain, then it cannot be part of a linear chain as well. 4 carbons. So I can either number it from left to right, or I can number it from right to left. Which direction prioritizes the alkyne having its lowest locant? Left to right? Both. I either put my alkyne at 2, or I put my alkyne at 2. So which way should I number it? When the highest priority is satisfied either way, when the highest priority functional group is minimized in either direction, then you prioritize the next highest functional group, which in this case is just the cyclopropyl substituent. You guys okay with that? If it doesn't matter which way for the alkyne, then just follow rules as normal. So what should we call this? 1 cyclopropyl . 2 what? 2-ine. Doesn't tell me how many carbons are in my alkane chain. 2-butyne. Or if you wanted to, you can call it 1 cyclopropyl but2-ine. When we talked about regiochemistry all the way back in section 2, boy, that's so hard to remember even. In our very first unit, the very first time we talked about regiochemistry, we introduced alkane regiochemistry. Primary carbons, secondary carbons, tertiary carbons, quaternary carbons, and methyl carbons. When we talked about stereochemistry for the very first time, we said R chiral carbons and S chiral carbons. Then we came back and we reviewed regiochemistry for alkenes. We said that alkenes can be mono-substituted, di-substituted on the same side, or di-substituted on opposite sides, di-substituted on opposite sides as trans or as cis. We said they could be tri-substituted or tetra-substituted. That was the regiochemistry of an alkene. And then we saw the stereochemistry of the alkene. We said alkenes sometimes have no stereochemistry. Alkenes sometimes have trans or cis, E or Z stereochemistry. When it comes to, have I been saying alkynes? Sorry, I get those, at this point, my words just fall out wrong. We talked about the stereochemistry and the regiochemistry of alkenes. Now we're looking at alkynes. They have no relevant stereochemistry. Their stereochemistry is that they are linear. That's the only thing there is to say about it. There's no R or S carbons on an alkyne. They're not even bonded to 4 distinct groups. There is no E or Z on alkynes because they only have 1 group attached to each carbon. So they can't have 2 distinct groups on both carbons. But the regiochemistry can be described. We can look at internal alkynes. This is an alkyne that has an R group on either side of it. And that means that we can have something like an asymmetric internal alkyne. The 2 carbon groups are different, but both carbons are equally substituted. Or we can have something like a symmetric internal alkyne, where both of the R groups are identical to each other. And if it's not internal, Yeah, external is not the word we're going to use. We're going to use terminal. External makes sense. That's the obvious choice. These terminal alkynes have at least one hydrogen attached to the sp carbons. Also, if that wasn't clear earlier when I said these are linear, that means that the carbons are sp hybridized. That I want you guys to think of those two things as the same, really. There is one very important terminal alkyne that's used as a precursor in organic synthesis all the time. That is a compound called acetylene. It has the chemical formula C2H2. Anybody ever worked with acetylene gas? Know somebody that has. Anyone that's familiar with welding will know acetylene gas. It's a very useful fuel. You could consider this like a di-terminal alkyne, right? This is the most basic alkyne there can be. But other terminal alkynes, you could have something like this. 4-methyl-1-pentyne. That's terminal because the second carbon is bonded to a hydrogen. Or I guess maybe I should say the first carbon is bonded to a hydrogen. So when it comes to regiochemistry, you can have something that's internal and symmetric, internal but not symmetric, or terminal, which will never be symmetric unless it's acetylene, in which case it is totally symmetric. It's actually a cool thing about acetylene. A lot of miners would use acetylene as fuel for their headlamps. They would take this, this mineral, this rock, calcium carbide. Carbide is C2 with what charge? Not 1. What's the charge on calcium? You guys are in OChem. You know your calciums, right? Calcium 2+, which means C2, 2-. So this is calcium 2+, carbide 2-. They would take calcium carbide, this rock that you can find mining, they'd put it down in this little chamber, and they'd have a screw cap above that they could release little droplets of water. And when this reacts with water, it creates calcium oxide and acetylene. And then that acetylene gas starts to leave the chamber, and they can light a flame. That little delta there just means heat. Light a flame and ignite the acetylene gas as it's leaving the chamber after it's produced. And of course you get carbon dioxide and water, but most importantly, you get a lamp. You get light that comes out of mixing water with this rock. Pretty cool. I don't think I would encourage you guys to do it because you're kind of strapping a bomb to your head a little bit. But then again, I wouldn't encourage you to drive a gasoline-powered car because you're driving a bomb. So a lot of dangers in the world. Okay. Let's talk about preparation of alkynes before we start looking into all of the ways that they can react. I want to remind you guys that previously we looked at ways to prepare alkenes. And we said that alkenes can be made by reacting an alkyl halide with a base, going through elimination. Or we could react an alcohol with an acid. And that specific elimination is called dehydration because it removes an equivalence of water from the molecule. To prepare alkynes, I can't do just one elimination. I need to prepare 2 pi bonds. So I need to do 2 eliminations. Here's how I want to set this up for you. The second elimination is what generates the alkyne. The first elimination then must have a group that can leave plus a hydrogen that can leave and a pi bond. And how does that pi bond form? Well, it forms just like we saw previously. It forms from a leaving group being taken off plus a hydrogen on a beta carbon, forming the alkene. Alkenes are precursors to alkynes, with a slight caveat. It needs to be a vinyl halide. There needs to be a halogen connected to the alkene. This is a dihalide, a dialkyl halide, but this is a vinyl halide. You guys see it? It's a halogen that's connected directly to an alkene. So not only do I need a base to run that first reaction, but I need a second base to run my second elimination. I need 2 equivalences of base. And eliminating from an alkane, an alkyl halide, is actually a lot easier than eliminating from an alkene. This requires a lot more energy. So what we need here is a strong base. All right, now to clarify a little bit about the ways that you can prepare an alkyne and the bases that you need. I'm actually going to show 2 different routes to get here. Notice that both of the precursors are dihalides, but their regiochemistry is different. What is the regiochemistry of the dihalide on the right? Sorry? Did you say anti? No. Okay. No stereochemistry, so we don't know really. What's their regiochemistry? We actually talked about this last week. Well, we're not looking at an addition reaction, so. Vicinal is one of them. Which of these is vicinal? The one on the right. This is a vicinal dihalide. So you can see that both the halogens leave along with the hydrogens that are at those positions as well. What about here? What's the regiochemistry of this dihalide? Geminal. Now on the geminal dihalide, the two hydrogens that leave are also geminal hydrogens. They come from the same position. So you can make an alkyne from a geminal dihalide or a vicinal dihalide. These are two possibilities. But what about the bases? You either need two equivalences of something strong, like potassium hydroxide, and heat. Delta there is just meaning provide heat. But what's even better than potassium hydroxide is having two equivalences of sodium amide or sodium hydride. Can you tell me why sodium amide and sodium hydride are better bases than potassium hydroxide? Doesn't have to do with dissociation of the ions. So like potassium hydroxide makes potassium ion, hydroxide ion. Sodium amide makes sodium ion, amide ion. Sodium hydride, sodium ion, hydride ion. Why is it that the bottom two, sodium amide and sodium hydride, are better bases than potassium hydroxide? This is what I would even recommend you use. Although you will see some problems that have potassium. It doesn't have to do with the number of hydrogens they have. It's true that they don't have an oxygen, but why does that make them better bases? Is oxygen not a good base? Think back to early on when we talked about caryo. Doesn't have to do about their priority. No. Induction? Induction might not be the right word because it's not attached to the molecule. So kind of similar, that there's no alcohol because it's not attached to the molecule. That is what it means to be a base. So that's true. That's just changing the language.
Is it because the base takes on rather than?
Do these bases have a different charge than this base? No. OH minus, NH2 minus, H minus. So they have the same charge. Is there any resonance in the conjugate acid? What's the conjugate acid of hydroxide? Water. What's the conjugate acid of amide? Ammonia. What's the conjugate acid of hydride? H2, hydrogen. So is there any resonance in any of those? No. Induction, these aren't really large molecules, so we're not going to talk about induction. Orbitals, okay, to be fair, hydride only has an s orbital, and amide and oxygen, they are probably sp3 hybridized, but it doesn't have much to do with their orbital. It comes down to atom. Hydrogen, electronegative or not? Not. So if it has a negative charge, guess what it wants to do? Share it. If it has a lone pair, guess what it's going to do? Take something. What about NH2 minus? Nitrogen, electronegative or not? Compared to oxygen, less electronegative. So why are these stronger bases? Because they're both less electronegative, more willing to share their electrons. Let's take a look at this table that I have linked on our homepage. If you come down towards the bottom, the only thing that is less acidic than molecular hydrogen are vinylic hydrogens and aliphatic hydrogens, sp3 and sp2. Here is something that is similar to an amine. So if I have an amide, I know that its conjugate acid has a pKa of 35. Okay, I want to give you guys some comparisons here. If I have H2O in the presence of NH2 minus, or if I have H2O in the presence of H minus, this will demonstrate why these other two are stronger bases than hydroxide. Notice that H2O has to be the acid. It has to be the proton donor. Because things that are more negative are often better bases. So what's the conjugate acid-base pair of the first reaction? H2O becomes OH minus, and we get ammonia, NH3. Proton donor, proton acceptor. What do we get in the second reaction? OH minus and H2. To compare acidity between hydroxide, amide, and hydride, I need to list the pKa's for everything. This has a pKa close to 16. If you look on the table that I have here, water is basically an alcohol. It's just not bonded to a carbon. It's inorganic alcohol. So it has a pKa very similar to the pKa of alcohols. I think water's actual pKa is 15.7 or 15.8, so let's just round to 16. Ammonia, which is very similar to this diisobutylamine, ammonia has a pKa in the 30s, close to 35. And hydrogen has a pKa in the 30s, close to 36. Remember that acid-base reactions are always in equilibrium. So these can react to form the products, but the products can react to form the starting materials. But equilibrium does not mean 50-50. Sometimes equilibrium is 99.9 to 0.1. Which way is equilibrium favored in these reactions? Why don't you guys all stand up? If you believe that equilibrium favors the products, move to this side. If you believe that equilibrium favors the reactants, move to this side. After this, you're going to get a break anyways, so you're moving now to get you ready for your break.
Your son.
I don't know, I don't remember.
You might be right.
Are you guys in the middle, undecided? Yeah. If you think that there is more starting material when equilibrium is favored, stay on this side. If you think there's more product when equilibrium is done, stay on this side. If you're not sure, come right here in the middle.
Oh wait, say that one more time, please.
Larger amount of starting materials at equilibrium, go to this side. Larger amount of product at equilibrium, go to this side. Unsure, come right in the middle. Okay. That's true, there is pretty full. Okay, you guys want to try and give an argument of why?
No.
Why do you think there's more of this at the product, or at equilibrium?
I don't really remember why.
Just going by the vibes?
I just think yeah.
So you think when hydroxide is in the presence of hydrogen gas, that they will favorably react to form water and hydride. Anybody want to give an argument for this side? Emma.
The PKA is more positive.
Okay, what does that mean? You just memorized the trend.
Yeah, I remember
Yeah.
that.
She memorized the trend that says more positive pKa, go to the other side.
That's my fault.
Or go to that side.
But the water gets used up, and so what's left over.
But then the hydroxide can react and just go backwards. So why do you think there's more of this at equilibrium?
That it's easier to have a negative hydroxyl and a negative hydrogen
Why?
because of just the nature of the atom.
Nature of the atom, that's fair. A negative charge on oxygen is more stable than a negative charge on hydrogen. Also, negative charge on oxygen more stable than a negative charge on nitrogen. Okay, what does the pKa tell you? Tells you how good it is at being an acid. More positive or more negative? What is a better acid? More negative pKa, better acid. When this exists, it's a better acid than when this exists. If this exists, it's not going to be an acid. But if this exists, it will be an acid. So you're mapping your pKa's so that you can say, this is going to do its job well. And when it does its job well, it doesn't exist. This is not doing its job well, which means it's going to be there quite a bit. Okay, why don't we take 5? And we'll come back in and we'll look at reactions we can do with alkynes.
Dude, I've been feeling so stupid lately. Like
Every day for me.
Oh, welcome to life.
So I'm in Chem 2, right?
Yeah,
It's my first ever fully online class.
that's hard.
And like,
I mean, we were technically right.
the material's easy to me.
Right?
I'm getting
Yeah,
on our
it's like,
chapter
I
quizzes, I'm
don't
getting
know.
99% because it's 10 questions, I just one. If I miss anything, it's only was 1.
Yeah, yeah.
My exams, I'm getting like 82 and 85, which is below the mean.
Huh.
I don't know if the mean is skewed because people are cheating, it's online fully,
Oh,
or I'm literally just missing it because like I don't know how I'm doing at these exams. Like, I just know if it was in person, I'd be fine.
sure.
Like,
Do you feel like the exam questions resemble the unit test questions?
yeah, I mean, yeah, I think the exam questions aren't bad at all. Then I check the answer key and like it says the stuff I'm missing points on. I don't even remember it really like being present. Like I'm missing stuff like it asked me for like, what was it? I'm just gonna pull it up. It was stupid. Like I don't remember these things even being present, or maybe I just like am going over it quickly and not reading it thoroughly enough or something like that. But like like Gen Chem 1, I was doing great on my exams. This class I did great on my exam. Like just
Gen Chem 2.
it's just I think it's just because it's fully online. I think.
So you're taking your test online, not
Yeah.
in the testing center.
Yeah, it's just online.
What if you put yourself in a testing environment that felt like being in a classroom or in a testing center?
Yeah, I think,
You know, like
I think
buckle down in the library and give maybe you have a time limit anyways.
It's 2 hours, yeah, but like I have more than before that.
Have you done Hess's Law yet?
That was
Gen Chem 1,
that was
I
Gen
think
Chem
it's
1,
Hess's Law.
Really? What was the 1 and 2 where you have to like put 2 equations together and cancel them out?
Well that is very similar, yeah.
Yeah, that code.
But you're going to do that a lot more in Gen Chem 2. You get introduced to it in Gen Chem 1.
Oh man, that code means
That's kind of like what we do with our mechanisms, you know? First, you form this intermediate, then that intermediate reacts, then that intermediate reacts. And if you cancel out all the things that are duplicated, you just get the overall reaction.
Like you can see the stuff I'm missing here. Like 0 out of 1 for excess concentration and H3O plus. When I got the moles of acid to base mix right there, and then here I missed another same exact thing but for pH.
So do you feel like you're being graded incorrectly?
I just think I'm being graded like, and there's like more particularly than I thought I would be. Like I don't remember. I don't know why I made it because 0 to 4 on question 2. I think that might have been multiple choice or something.
Interesting.
And like if I go down, there was another thing that I got wrong that I messed up on. Right here, moles of fluorine. 0 to 1.
Moles of fluoride,
Fluoride, yeah.
but concentration of fluoride.
I got right.
It's almost like your partial credit. You're actually losing points for your partial credit
I feel like I'm.
for not showing your. Like these are the things that I would look for to give partial credit to someone. Oh, they got the concentration wrong, but they did have the moles earlier, so I'll give them partial credit. But here it's like you're being graded for it.
It's like I have the mole, I have the concentration, right? Which
You can't get the concentration unless you have the moles and
and
the
the
volume.
volumes. I'm like, I don't understand how I'm getting that right.
So
but it's
unless
just
the
wrong.
question, I don't see the questions here. So unless the questions are being phrased like, show the moles of fluoride, the combined volume, and the concentration.
Let's just take a look. Lockdown, bro.
Yeah. Yeah, that's
Maybe after
that's how I
class.
felt.
I'll do that. I'll have to do that. But yeah, it's just pissing me off.
Yeah.
So,
Yeah,
Wait,
I hear you.
About halfway out.
Yeah.
Where's your
I just must have standards.
Wait, really?
Yeah.
That's who I had. Wait, that's so weird.
yeah.
For chemistry?
Yeah.
Oh, I love him.
I just, I mean, I'm online is just not meant to be as that.
I can't decide.
We were in the same 80% class.
I have it fully online, and I'm like, I mean, I don't think going to Zoom's
By the way, guys, that concentration gradient that we had in the classroom, that was like almost exactly the concentration gradient of this equilibrium.
Oh, you're welcome.
We did it on
That's
purpose.
what you were doing. I knew there was something.
There you go.
If you had 100 molecules of these reagents, 99 of them are going to sit on this side. You've got that 1% chance that it's sitting over here. You can actually calculate the equilibrium gradient by doing 10 to the difference of the pKa's. That's really that's tripping me out for a second. So maybe not 99 to 1, but more like 9,999,999,999 to 1. 10 to the 20th. I guess that's more than 9 billion. That's like, you know, I don't even know how to say it. 900 billion to 1.
We didn't actually.
No, we were close though. We were about as good as we could get for this sample size. So for every one molecule of reagent that you would have, or reactant on the left-hand side, you'd have 900 billion molecules of the products that exist in solution with it. So these are much, much stronger bases compared to hydroxide. Because when hydroxide is in the presence of them, it doesn't even react. But when they are in the presence of water, there's a very favorable reaction. So you guys understand why it makes sense to use much, much stronger bases. Bases that are 20 orders of magnitude more acidic, not 100 billion times more acidic, or sorry, more basic, rather than using hydroxide. It doesn't mean you can't use hydroxide, it's just not favored by equilibrium.
Could you explain the chiral reaction part again?
The chiral.
Like, what atom being the chiral is like?
C is not chiral. Wait. Oh, in karyo.
Interior.
Sorry,
Sorry.
I was hearing chiral.
I was saying chiral.
Chiral. I think you'd have to switch the A and the R. But actually, that might be a good way to remember it. Because what does karyo mean? Anything? No, I don't think so. All right. What the A means?
Or just what it meant like in years.
Yeah. C is for charge. A is for atom, which actually has two different meanings. If you're comparing atoms that are in the same row, horizontal to each other, you look at electronegativity. But if you're looking at atoms that are in the same family, vertical to each other, you look at size. More electronegative, more acidic, less basic.
Okay, so we're still looking at this molecule and seeing what's more acidic and what's better base.
True. Yeah. And we're saying this is less acidic, pKa at 35. This is more acidic, pKa at 16. So Bad acid, if it forms, it doesn't act as an acid. Good acid, if it does form, it acts as an acid right away. And then conversely, negative charge on a more electronegative atom, weaker base. Negative charge on less electronegative atom, better base. Resonance, meaning resonance always stabilizes a charge. So if you have a positively charged product, conjugate acid, and it has resonance, it's less acidic. Or a negatively charged product, a conjugate base, and it has resonance, less basic. Induction, which is a push and pull of electrons, so you got to think about electronegativity. And orbital just means more S character, more acidic, or more S character, less basic. And we're actually going to look at that next when we look at reactions with alkynes.
Okay, but first, I want you guys to try and solve this for me.
Can you give me a precursor that reacts with two equivalences of sodium hydride to give me 1,4-diphenyl 2-butyne? I'm going to give you one hint.
Try to map your carbons.
Notice that I'm just counting the phenyl groups as atom 1 and 6. But if you map your atoms, you have a better chance of predicting the structure correctly. Good. Are there any others? Now, if you think about comparing this to this, it doesn't look the same, does it?
No, I haven't adjusted.
But it's not your zigzaggy. No. It's that this has one leading group halogen and one hydrogen. You have two halogens.
Oh, I went all the way back.
You did not go all the way back. What you would need to do is actually, there you go. Now you've gone all the way back. Oh, I was like, that doesn't look good. We're trying to find a starting material that can react with two equivalences of our strong base, sodium hydride, to give us this alkyne, 1,4-diphenyl 2-butyne. So we just need to know, how do you prepare an alkyne? How will you make that? You know your carbon chain is going to have those 6 carbons. So start there. Sketch out those 6 carbons. Then figure out, where do you want your groups to be to do your double elimination? Carbon rarely bonds to sodium. But sodium is not the same as what we would say over here, like X. What you would want for X is a halogen. Oh, I don't No, these are perfect actually. This works as well, but I'm going to demonstrate how this can also give us a different product. Sure. So you've got your right carbon chain. You've got two groups right where I want them to be. I just want them to be different groups. So rather than so. We don't know what the X is. And you can pick one. Yep. Okay. Pick your favorite. I've got one favorite. Do you notice how your phenyl groups change positions? Your product's got phenyl at 1 and 6. So your precursor should just look the same when those phenyl groups do. We want to do some chemistry around 3 and 4. So we got to figure out what should be on 3 and 4.
I was just copying.
That can be removed
I was wondering if that was
so that we can make our alkyne.
We think you're the one that's in red.
It's a good start. You got to copy down.
I think.
Also a good start.
Like
We
what
want
are
our
with the
reaction to go around 3 and 4.
Yeah, well, because
So what do we need to add there that can be
Yeah,
removed?
I think
it's the same thing.
it's the intermediate or something.
You're close. I
Yeah.
think you're missing.
Wearing like,
Um,
instead of having the 2 halogens, like on one instead of.
No, I think you got it right. Now you just need to figure out how to.
That's on 3 and 4, right? It would be on 3 and 4.
Yep.
What'd you draw?
That works, and that does. We're going to talk about why that might be problematic, though.
On this. Could
This
it
one.
be either way, like this?
I mean, that's true. Yeah, you're.
It doesn't
It's
matter.
actually the
because-
exact same
Okay.
molecule, but there's a problem about the product that forms. You shortened your carbon chain a little too much.
Okay.
Notice you've got phenyl is 1, 2, 3, 4, 5. Phenyl is 6. Now you've got 1, 2, 3, 4.
Okay, that's what I was thinking about.
So you need a few more atoms, and then the placement of them might need to change as well.
Okay.
So yeah, this is the other one.
Is the final
There is a problem
or is it just
about reactylase 1. It doesn't just form this.
Well, it might actually.
This is great. These are exactly the same.
Oh, yeah.
They're not different. And this is a good answer, but we'll talk about what other issue we can come up with. Good, you got your carbon chain down. Yep. And you know you want to do reactivity around 3 and 4.
I thought this stuff's
Close, but I need to do the 2 eliminations.
It's like
See in red I've got now. I need to have 2 groups that can see.
I didn't
And then we
have a
talked
problem
up
with
here
it.
about how those 2 groups could
Just have one just high, but
form the 2. They need to be
I love ginger.
good.
was way better.
And now there is
so
another.
fun.
There's another
It's like
precursor
physics
that's
one.
coming.
This is not.
But I
I think I graded.
Another structural isomer.
Very
Yep,
thinking about how you
that's great. That's exactly what it is.
Sanders.
But the thing
Yes.
is, so like on
Perfect.
Zooms and stuff, like,
And now there is,
like, how
both of you have the same one. There is another precursor that can work as well. Jones.
So I'll show you what
In between?
Yeah, yeah, yeah.
Okay.
You don't even have a carbon chain yet.
I'm
Map out those carbons. Just draw.
trying.
Just draw that 6 atom chain. Good, good. Yep. And this one we'll talk about is a little problematic. These are exactly the same.
Right.
No difference.
You imagine?
Any halogen. Yep. Can't be an alcohol. Good. And there's another one. Good. And there's another one. So you need to have 2 leaving groups. You've got 1 at 4. We also need to do something at 3. So maybe put your second one at 3. All right. So our 6 atom chain is where I'm going to start. I'm going to put my phenyl and my phenyl, and I'm going to map these so that we can see what we're dealing with. In order to prepare an alkyne, I need to do a double elimination. I need 2 groups that can leave. When we did alkenes, we said the leaving group can be a hydrogen and a halogen if we react with a base, or it can be a hydrogen and an alcohol if we react with an acid. When we looked at alkynes, did we say that alcohols can be used as a precursor? No. The only option I gave you was a dihalide. So you can't use an alcohol, but you can use a geminal dihalide or a vicinal dihalide. Notice that the vicinal dihalide, the 2 carbons of the dihalide become the 2 carbons of the alkyne. So if my 2 carbons of the alkyne are 3 and 4, then I want to have a halogen on 3 and a halogen on 4. And also the hydrogen on 3 and the hydrogen on 4. Those are removed as well. So this becomes 2,3-dibromo, 1,4-diphenylbutane. 2 equivalences of strong base forms the alkyne. I could have had another precursor as well. I'm going to map my carbons once again so that we can see what we're talking about here. Instead of having a vicinal dihalide, I could have had a geminal dihalide. I like bromine. I'm almost instinctively always putting bromine as a leading group, but this could be chlorine or iodine as well. So I'm putting chlorine here as a geminal dihalide. And whether I put them on carbon 3 or carbon 4, they're actually the exact same molecule. They are not structural isomers. They're not stereoisomers. You're just looking at it from a rotation of the molecules perspective. So 2,2-dichloro, 1,4-diphenylbutane. That also gives me the final product. The issue is this can give me a different alkyne as well. To give me the alkyne I wanted, I needed to remove the 2 hydrogens from carbon 4, adjacent to carbon 3. But what if I removed the 2 hydrogens from carbon 2 instead of carbon 4? One, two, three, 4, 5, 6. A bit of an issue in terms of synthesis. This alkyne has 2 precursors, but one of those precursors gives 2 alkynes. So if I wanted to synthesize this alkyne selectively and not get impurities, not get byproducts, not have to deal with this elimination, giving me 2 different structures, this is the preferred starting material. This one, less preferred.
So, like, what's the mechanism here? Like, are we saying that the bromine, the 2 bromines are electrophiles, and they are, I guess I'm wondering how this pi bond is forming and where those electrons are coming from.
Okay, this is not a mechanism that I'm going to test you on, but if you want to see the mechanism for how bonds are breaking and forming, I'm happy to do that for you. And what I want to start with is the geminal dihalide. Or sorry, vicinal dihalide. H minus is a base, which means it's going to look for a hydrogen. So H minus takes one of these hydrogens. Remember, when a bond breaks, it breaks towards the more electronegative atom. The CH bond is breaks towards the carbon. That carbon pushes it into a double bond. That's going to break the octet of the adjacent carbon, so the adjacent carbon kicks off its bromine. This is why we call the bromine a leaving group. It gets ejected from the molecule. Notice that this created a double bond, but leaves a bromine and a hydrogen on adjacent carbons. This creates the vinyl halide intermediate. What else does it create? Well, the conjugate acid, H2,
the ion Na plus and the ion Br minus, sodium bromide. But don't forget, I said that there were two equivalences here. So now, the second equivalence of sodium hydride, you know what? I'm going to rewrite that second equivalence on the other side. The second equivalence here takes the second hydrogen, CH bond breaks, forms the second pi bond, kicks off the second halogen. Now I have a triple bond, and I have two equivalences of NABR and H2. Did that clarify it? I know some people, the mechanism makes it make sense. Other people, the mechanism makes it make less sense.
I guess my brain is just stuck in what we've been doing, for the last week or so.
Addition reactions,
Right.
which is the opposite of elimination reactions.
Okay.
Addition reactions take a pi bond and use it to bond to something else.
I've almost been looking at it like fuel or a battery that allows you to do it because of the energy that's in that pi bond. But we're doing the opposite here.
We're doing the opposite. We are creating a pi bond by removing groups.
And that power or the energy that allows you to remove is the base.
Yeah. It's the base taking this hydrogen. And remember, bonds break towards the more electronegative. So carbon takes the electrons, and bromine takes the electrons. Because the CBr bond, bromine owns. So bromine leaves as Br minus, bromine leaves again as Br minus.
So this isn't electrons being pulled or pushed as much as it is the base is taking that hydrogen and that's releasing the electrons.
Yeah, there is a pulling and pushing. So remember, you're still going to heat this reaction. You're going to get those molecules moving really fast because they need to ram into each other with the right energy in the right direction. This hydride needs to run into this hydrogen with such force that the bond breaks back to carbon, which forces the bromine to kick off. There's a lot going on there. That takes a lot of energy. I would be cautious about saying addition reactions, the pi bonds act as like a fuel, because you are always boiling these types of reactions. You're always providing a ton of energy. So the fuel actually comes from heating the reaction. But you've got different bonds that have different bond strengths and energies and stuff. That's elimination. Double elimination.
So the other one is technically NH2 and heat as well.
You could have put NaNH2 as here.
Right, like from the viewpoint KOH and heat, you're meaning and heat also on the other one too?
So this is an interesting thing. Heat is not always implied in reactions, even though heat is often required for these types of reactions. When heat is when heat is explicitly stated, what it means is that this reaction really depends on providing the right amount of heat. When heat is not explicitly stated, it's almost always still necessary. And there are some reactions that you'll learn that you put over the reaction arrow, negative 78 degrees Celsius. You run it at extremely low temperatures because too much heat doesn't give you the reaction you want.
So when you actually show heat, you mean
A lot of heat. Yep. Like you're not getting any good amount of product without that heat. All right. This is how we prepare alkynes. I want to give you one last question on this, which is, what alkyne forms in this reaction. You know what? We're actually going to do, so I want one alkyne that forms here. And then I want two alkynes that form here. It is drawn in a way that I wouldn't think there are extra carbons, but it's still not linear. You're up to about the top one. You're missing. Actually, you've got the right number of carbons, but you're in the wrong place. Yes. Are you mapping your carbons to help you keep track of where things are? Good.
Just one.
That's one of them.
Oh, yeah.
One too many carbons out here. Those are both correct. One too many carbons out here. Those are both good.
You can use the carbons.
If you want to, when I say map, I like to say there's a methyl coming off of 2. So you don't have to count that one as well. Okay, that's a question.
So 2 iodines on top.
Yeah.
If they can't go to the left because that can't be linear.
Yeah.
Right.
Well, correct. It doesn't have 2 hydrogens to give away. Yep, gotcha. That's exactly it. Good. Yes, those are the
It's
2.
that point in the semester, run out of.
Okay. We're not going to have time to look at reactions with alkynes. That's what we'll pick up with tomorrow. You guys know we don't have lecture on Thursday. Sucks. So we're going to do reactions with alkynes tomorrow, and there's a lot of them. And if we have time to, we're going to start looking at reactions with alkyl halides as well. That sets us up for all of next week being on substitution, elimination, and Diels-Alder reactions. And I think we can get through them because we're actually learning about elimination at the moment. And it sets us up for some easy stuff later on. A lot of you, I noticed, got this bottom one correct. You recognize that the alkyne could form symmetric between carbons 3 and 4, or the alkyne could form asymmetric between carbons 2 and 3. Both of those are possible products. Now on the top reaction, because there is a geminal dihalide, we could take hydrogens from the tertiary carbon on the left, but there's only one hydrogen there to eliminate, which means it would stop at an alkene. You can't eliminate further to an alkyne. So instead, we'll eliminate from the carbon on the right, which gives us this. What I noticed in a lot of your answers was that you maybe miscounted your atoms. I saw a lot of answers that had an extra methyl group coming off of carbon 5. So when you're mapping, just be careful. You don't have to number every atom. Maybe you don't even want to use numbers. Maybe you want to use different symbols, star, dot, square, triangle, to keep track of all of the different atoms you have. Good work. Get a head start on this next unit, Unit 9, or Section 9, homework, because we'll be done with it tomorrow and moving on to new stuff. Okay? Have a good night.
John, how similar